this is boring. I mean, not the actual slide, but I'm actually running it in Firefox. And that's not cool. Well, you know the saying that Vim is a great editor, it just lacks a good operating system. Well, the thing is, I actually have Emacs. And Emacs is a proper operating system these days. So I'm going to try something new. I'm going to try actually just running my slides from Emacs. So these are Reveal.js slides. And I should warn you, this thing is extremely unstable. It actually just crashes randomly at some point. So if this goes boom, well, that's part of the excitement. Let's see. Emacs. Where is it gone now, Vimisa? Right. So so I figured since my language isn't really quite as clever or as finished as the previous languages, I just do a talk on essentially how I built it. So the idea is that I'm going to try to show you how to build your own Lisp, which is kind of a traditional rite of passage for most developers. In fact, if you look at GitHub, well, actually, if you look at GitHub, GitHub's most frequently repeated projects, you're probably going to find something like async control flow libraries for Node, but then toy Lisps are probably going to be number 2-ish. So why would anyone want to do that? Wait, I lost the focus. Emacs, please work. So why would anyone want to do that? Well, first of all, because it can. But from a more personal perspective, I have this idea about the perfect language. And the perfect language is Clojure. Bear with me, please. Clojure is, for a start, is a Lisp. And Lisps are just, I mean, we have like a 50-year tradition of Lisps being beautiful, elegant languages. It's extremely powerful, and I mean, it gives you unprecedented metaprogramming powers. And Clojure in particular is, I'm looking at Rich, I'm trying not to yeah. It is just so perfectly designed that I mean, even though it lacks a type system, you can't really go wrong with Clojure. So the perfect language is Haskell. Haskell, what Clojure aspires to functional purity, Haskell is actually completely uncompromising about that. And it has an extremely powerful type system, so powerful that as long as your Haskell program compiles, you can be pretty sure that it is bug-free. It doesn't mean that you got the program that you thought you were writing, but it's going to be a correct program, at least. So Haskell just fills me with thoughts of warm, fuzzy things, which are called monads in Haskell. Now, the problem is that we have a bit of a logical dilemma here, because both Clojure and Haskell are, in fact, the perfect language. So I figured that the actual perfect language would be something that kind of combines the two. And well, thanks to Michael Fogers, who has been oft quoted here today, I discovered a language called Shen, which had me extremely excited. It's got S expressions and macros and all the metaprogramming powers that you would expect from a Lisp. It's got pattern matching, which Haskell gives us. Just by far one of my favorite control structures. It's got a very advanced type system. It's in fact a Lisp with a proper type system. And it's even got a logic engine. Would you believe that? It's got this kind of prologue thing embedded inside it. So this has got to be the perfect language. So I started having a look at it. And I found that it has a cumbersome syntax when you want to be a bit more complicated about your type systems. It's got a strange license that a lot of people are complaining about. Now, I could deal with those things. I mean, syntax is just syntax, right? And licenses, we can just pretend they don't exist. I think. But the worst thing is it's actually got mutable data structures. And yeah, mutable, you just don't do that. So sadly, that just turned me completely off Shen. I mean, it's to be fair, it's definitely a brilliant language, but it has these things that just don't click with me. So what is one to do? Well, obviously, you write your own language. So I just sat down one weekend and started writing a language. It's pure, like Haskell. It's immutable, obviously, like both Clojure and Haskell, and all languages should be. It's homoiconic. It's more or less a Lisp, at least. It's typed, or at least it's going to be when I finish the type system. I discovered that writing Lisps is quite easy and quite quick, but writing type systems, that's a whole different story. So I wrote BODOL in the status in about right now, in April. And since then, I've been working on just trying to figure out what to do with the type system. I wrote the actual BODOL in about a weekend. And I've been using it 3 or 4 months since then to just get my head wrapped around type systems. Types are hard. And the best part of BODOL is that it actually uses Unicode characters in the syntax. And BODOL had its time on the Hacker News front page. And most commenters decided that because it actually used characters outside the ASCII character set, that was extremely irresponsible, and it was bound to fail. So that was quite reassuring. So this is what BODOL actually looks like. You'll notice the Unicode characters there. We got the floor in, which is essentially defining a named function. You got the arrow there, the right arrow, because arrows are beautiful. It also saves you a character compared to languages like Erlang, which use the minus and the, what's that, greater than, to simulate arrays. But hey, this is 2013, right? We can use Unicode now. So you notice that it's got pattern matching, much like Haskell. And apart from that, it looks quite a lot like a Lisp. This is functional hello world, the factorial function. I could have done regular hello world, except that BODOL doesn't actually have I/O yet. So you can get fancy with the pattern matching. This is an implementation of a map function. A bit naive, perhaps, but it works. It takes a function and a list, and if the list is empty, then it just returns an empty list. And you'll notice the kind of destructuring of the dotted notation that pretty much exactly like Haskell to iterate over a list. So you get the head and the dots and the rest of the list, essentially. So this is quite traditional. Let's just see if we can get this to run. Because this is Emacs, right? This is the good part. So I'm just going to fire up an inferior Lisp buffer. Woo! That was, of course that couldn't work. That would have been too easy. So why is it actually, wait a minute, let's try that again. Still doesn't work, and I have no idea why it's trying to run lining in instead of actual BODOL. Never mind. So you're just going to have to take my word for it that these functions actually work. Doesn't really matter. Oops. So So how do you actually build a Lisp? This still counts as my little coding background, so I'm being consistent here. Well, first of all, you're going to have to pick a language to implement it in. And you're generally free to pick any language you like, as long as it's Clojure. You'll see why in a bit. Well, actually, what I discovered while building BODOL is that it really helps to cheat in the initial phase of development if you're actually writing your Lisp in another Lisp. For one thing, I used Clojure as a parser for the longest time. And that really brings me to the first topic of the day, parsing. That's really where you have to start with any language. And there's this thing for Clojure called instaparse, written by Mark Engelberg, which is intended to be kind of a universal parser. I think its idea is to try and make parsing as ubiquitous as regular expressions. It's a fairly efficient GLL parser, and it uses just essentially a plain EBNF syntax that's extended Backus-Nor form. And of course, if you're Daniel Spivak, you could use parser combinators instead. It's a very flexible library. But we're going to stick with the Backus-Nor. Oops, I'm going too fast. So I have some code for you, if I can find it. I think I'm actually in the wrong project. Yes, I am. So presenting from Emacs is actually hard. Would you believe it? Here's my project. And here's my instaparse. So I'm going to see if I can get, yes, an nREPL buffer. So I'm going to compile this. I'm going to go here. And I'm going to give you an example of instaparse. So I'm going to define a parser. I'm going to use instaparse to define it. And so I'm going to just write a very simple parser for a very stupid toy language for you. First of all, we need some white space. And you can use regular expressions to define those. So this is going to match just a bit of a white space. And I want numbers. And numbers are, of course, defined like this using regular expressions. And so I'm going to make an expression room, which can be, let's say, a number at first. Let's see if we can do something about this. Wrong number of arguments. Really? Parser. Right. So this should let us call a P. Insta/parser is a function that will return a parser function, which I can just call. And so if I provide a number, let's go bigger, you'll see that we get some kind of a syntax tree. The expression matches the expression rule, and it contains a number with the value 1337. Now, usually we don't want to see the number thing here on the space for that matter. So we use the angle brackets, is that what you call them? We use those to tell instaparse that we don't care about this part. So we get a clean syntax tree. In fact, let's just hide the lot of it. So that's a syntax tree for just a number. Let's just, we're going to have some S expressions, right? So parentheses are nice. And we need something to put in there. First of all, we don't care about the parentheses, so we hide them. But we need some kind of syntax for some kind of operation. Let's do add. And it's going to be a space and a number and a space, and another number. And so this could be an add room. So we can do add 1337. Ooh. How come that doesn't work? Huh? Oh, sorry. Yes, of course. Thank you. So now it passes. Now we see that we don't care about the white space at all. We're just going to hide that. So that's a simple parser for you. That gives you at least an idea about how instaparse works. Now, let us see if we can find a bit more of an advanced parser for you. So this is Bodil's parser. You see, it's not very big. I mean, it's definitely more complicated than what we just did. But this being something like a Lisp, it's got a very simple syntax. So we got about a page full of rules, page and a half. It's a little more complicated than a regular Lisp because I decided that functions are actually going to be syntax and not just lists as in regular Lisps. But there you go. It essentially works the same way. Let's see if we can make that run. So where did my REPL go? There we are. So much the same thing. We define a parser. And let's do some BODOL code. Let's do a lambda, takes a number n, and returns an increment in n. So that essentially gives us the AST for a BODOL program. So that is extremely uncomplicated. You can do this now, right? You can just go home and at least write a parser. So let's take that further. Where did my slides go? There we go. So another thing you need is primitive types. By that, I do not mean types in the type system sense, obviously. I mean runtime types. Like strings, numbers, booleans, symbols, this being a Lisp, it's got to have, would it be right to call them first-class symbols? Let's call them that. And this isn't strictly a primitive type, but it's kind of important because our code is built out of constants. Constants, in this case, of course, are immutable. Apart from that, they're the traditional constant. We don't care about creating extremely efficient data structures at this point. We just want to get the language working. So we're going to try constants. So I am going to show you. I'm still, oh right, I see. Emacs is complicated. Don't tell him anybody. Types. So quite simply, I define the basic data types as implementations of a protocol called ltype, which simply provides the interface for getting a value out of it. And I got some fancy macro stuff going on up here. So I create booleans, numbers, strings, and symbols. They're very easy. They only essentially contain values. And I got the constant down here. Implements much the same interfaces, but it's a lot more complicated. So compile, switch namespace. I can do things like creating a number. This is what a number representation inside the Bordo runtime looks like. And same thing, etc. I can do consing. So that's the dotted form, and I can also, of course, keep consing them together to create lists. There's a list with two numbers. So this is going to be your basic building blocks. You actually want the parser to, let's see, wait, gotta do this right. You actually kind of want, right, parser. Let's do it like this, if you're going to be difficult. You kind of want to transform the thing that comes out of interparse into your data types. So I got something to do that. I got some code up here I could just reuse, I guess. So I got a function called parse, which instead of the AST, it actually outputs BODOL data types, this being a function. So once you got that sorted, you can start building the actual language runtime. So you're going to have to start with evaluation. And essentially, your eval function is going to take a program and an environment in, and it's going to output a result of the evaluation, and it's going to output a potentially changed environment. So, incidentally, what does this look like to you? What would be a great way to implement these two steps? Monads! You should know this. Actually, this is almost exactly what a state monad does. You have a function that creates a function that takes some state and performs a set operation and returns a result and some new state. Also, monads are awesome, so you kind of have to use them. I keep doing this, sorry. Monads. So the idea here is that you can have, let's say we want an operation that defines a symbol in the scope. So we take a symbol and a value, and we return a function which takes some state. Let's call that the environment, is really what it is. And it returns a list that contains a result. And I think for this example, we're going to make the result just nothing. And it takes a changed environment. So we have the option of, because the environment is being passed in, we have the option of changing it. Actually returning a changed environment, not mutating the actual environment, obviously. So we just add, we suppose the environment is just a map, and we add the symbol and its value to the map. So if we call that, let's say we do keyword foo 1300. So that returns a function. Let's call that function with some initial state. Let's just use an empty map. And you see that we get a result back, the one that we specified, and we get a new environment with the value set. So this is a basic state monad. Let's add one that actually performs a calculation. One that just adds two numbers together. Same format. This is just basic state monad stuff. But here we actually return a result which is nil. We perform the calculation, get env a. So the idea is that we pass two symbols in. The add operation is going to resolve the symbols from the environment, and it's going to return the result of adding them together. We're going to assume they're the numbers. And we are not going to change the environment for this operation, so we just return it as is. So let's create a program. Now I got some monad helper functions that generally runs through all of BODOL. we got reduce state. This takes some initial state, and it takes a series of state monads, or monadic values, and runs them as a program in sequence, and passing the new state along as it goes. And it finally returns the result of the final operation. So this should be a list. We can add foo to the environment. We can add bar to the environment. I think you see where I'm going with this. So what's this going to do? You guys are so clever. So this essentially does some kind of a reduction on this list of monadic values. And essentially what it does is it evaluates the program. And it totally doesn't work. I just realized. I forgot something, didn't I? Why didn't you guys put this? You're very bad developers. See, now it adds it together. And you notice that we have added both foo and bar to the scope. And at the end, we do the add, and that is the result right there. So that's how to do program evaluation using state monads. And the great thing about that, of course, is when you're writing a language that's supposed to be pure, it's kind of important, at least for your heaps of credit, that your implementation is also equally pure. So BODOL is insistently using state monads instead of any kind of mutable state, because mutable state is unnatural, as we know. So, next slide. So there's this thing called scoping. And we want lexical scoping, which means that a function's outer scope is a code around it, not where it's invoked from. That would be dynamic scoping, and that is stupid. I mean, what are we, Emacs Lisp? So that brings me to functions, by the way. I'm not going to go too deeply into this, but I am representing a function in BODOL as its own data type. So it is essentially the same as my primitive data types. It uses the same protocols, except it's a bit more complicated. And you notice that when I create the lambda value, I pass it a scope when I create the value instead of when I invoke it. That's what makes the difference between lexical and dynamic scoping. I created a toy Lisp earlier where I actually made this mistake, figuring that when you want to call a function, you just pass the current state to the function, and the function does whatever to the state, and you return that. And that doesn't read well. Dynamic scoping means that it's hard to see where your outer scope comes from, and so it's harder to reason about it. This is why lexical scoping is good, and I'm very glad that Emacs Lisp is actually giving you the option now of doing both. I hope that they will eventually get rid of dynamic scoping because it's stupid. I mean, even JavaScript gets this right. So, well, kind of right, at least. You still have to deal with the function versus block scope thing, but that's another story, another language. So, evaluating a function. When you're evaluating a number, it's quite easy because the result of evaluating a number is the number. And same with strings and booleans. Functions, though, actually do things. So, yeah, you can see there's a lot of code here. It's complicated by the fact of pattern matching, but never mind. So, yeah. What can I say about this? So when I evaluate the actual lambda, which is represented in the syntax tree, you'll notice that I bind the current scope to it. This is kind of compile time, you could say. This is what gives us lexical scoping. I bind the scope when the lambda value is being defined and not when I invoke it. And this being a Lisp, I still evaluate constants, where the lambda is wait, this is wrong. So a lambda is still represented by a list in theory, which allows, hopefully, later macros. So you have to deal with evaluating that, and I'm going too deeply into this. So let's get back to the slides. Pattern matching. I mentioned pattern matching. And of course, the smart thing at this point will be to actually read Luc Maringer's paper, which describes how to create a very efficient machine for doing pattern matching. And Clojure's core match library actually uses this to good effect. However, we are lazy, so we are going to use core.logic instead. We're just going to run star that shit, because it's so much easier. So let's do some core.logic. David Nolan couldn't make it, strangely, so I'm going to have to try and fill in. Pattern matching. OK, suppose you have a function like this. I like series. So we want to match the first case if you call a function with the function with both zeros as arguments. And we want to match a 0 and whatever and 0, and the catch-all case at the end. So let's create a program for that. We care about 3 values in this case. We care about the match itself and the A and B values, not A and B. So what we're doing here is we are just plain unifying the terms that we're interested in. So let us start with a match. 0 and 0. 0 and 0. So that's what we're looking for, and then let us imagine that we are calling this function with 2 arguments that we just unify this with. Let's say we're going to go for 0 and 1 and see when we get a match. So is this going to work, I wonder? Oops. So, oh yeah, that's how I did that. Can you actually see the result at the bottom? In the back? It returns an empty result, so that means the match failed, which means that we move on to the next clause, 0 and A. Let's match our result with that, and we get a hit. So if you can see the bottom there, we see that this is the whole match, and A has been assigned the value 1, which seems right, and B is unused. So we got a hit. And this is essentially the cheap way of doing pattern matching using core.logic. You just keep trying the rules until you get a match. Of course, at the end here, we will get a complete match on anything. We just say that A and B equals essentially the arguments being passed in. As you see, they are 0 and 1. Pattern matching. It's horribly slow, but yeah, this is a prototype language, right? We don't really care at this point. But core.logic is fun. That's what I meant. So, type systems. How are we doing for time? I think we're pretty much out of time, but I think we're just going to keep going. Type systems are really easy, because I'm just going to do some more core.logic for you. I'm going to do type inference in core.logic. Because that is cool. Suppose you have a function like this, the successor function. Simply takes an argument and it increments it. So what can you tell from this function? what would the type signature be? Takes an int, returns an int, or a number. So, core logic up. So the suc function, successor function, that's what we're interested in. We want this to be a type signature. Let's introduce some more variables that we don't care about the results of. They just have to be there. So a and b and plus. A being the argument, as above, b being the result, and plus being the plus function here. The plus function is implicit, it's defined in the scope. So we just say that plus is a function that returns a and b. So the successor is also a function that, that takes a and returns b. And I'm doing this in the wrong order. So we see that plus is being called here with a and b. B being an unknown. We just have to assign them a symbolic value to the 1. So we know that plus has a type signature because it's already defined. So we assume that this has already been inferred. So we know that this is a number. It takes a number and it returns a number. And now we know that we are using, we're calling suc with a as input and b as output, a and b being symbols that are supposed to become types. And we see that we are calling plus in the same way. And we know this type signature of plus. So this should actually let us infer the type signature of the successor function. Namespace not found. What's that? I have to combine. Oh, look at that. Oh, wait. Sorry. Parenthesis bug. This is a common Lisp problem, don't worry. So we see the result down here is a function that takes a number and returns a number, as we can tell ourselves. So that was type inference, done very, very, very simply in core logic. You can get more fancy, of course. My idea for BODOL right now is to just implement a basic Hindley-Milner type system, because I'm not very smart, and Hindley-Milner is easy to implement. So I thought I will also show you my Hindley-Milner implementation, but I see that we are way out of time. So we're going to skip that. See what's on the next slide. Yeah. So the hardest problem in computer science, and this is usually the one that you run into at the end when your language is ready to be released. You have to find a name for it. You'd be surprised how difficult this is, because there are so many languages out there that just about every name in existence is already taken. Now, some of the traditional approaches, which I'm going to list for you. Yeah. So you can just go down the list, essentially, until you find a good name. You can steal some person's name. That's very popular. You got Haskell, for one thing. You got Erlang. You got lots of famous people's names being recycled for names of computer languages. Just make sure that you don't pick somebody still alive. That's kind of creepy. No, really. I mean, Bordo was originally going to be called Oleg, but I figured that wouldn't work out. But Oleg is awesome, so yeah. You could go with a general computer science concept, like say if your language uses closures, then you could call it Clojure. You could just take another popular language and add script at the end. In all fairness, that wasn't Brendan's fault, but There you go. You could just take a letter and increment. So C is kind of the successor of a language called B. And I think we're at J now, right? So you can just take that and keep going. Or you could just name it after your favorite pony. That was what I originally intended to do. And of course, Rainbow Dash is best pony. So I figured my language could be called Dash. Problem is, of course, that all names are already taken. And Dash was in fact taken by Google for their attempt to replace JavaScript. Now, apparently, there must have been some kind of trademark infringement lawsuit or something, because they actually renamed it to Dart, which is not best pony, but there you go. At least I couldn't very well call my language Dash because of the association with that other language. So, yeah, you could go with something from this list, but whatever you do, make sure you just don't name it after yourself, okay? Right. I think you're ready now, so go forth. 2 languages. That's a good one. Right, so I expect to see a multitude of new toy Lisps springing up after this talk. So enjoy yourselves, and thank you. So links, the first GitHub link is for the slides. It also includes BODOL. It's what I've been using. And the second link is for BODOL itself, if you want to look at it. I'm guessing we're way out of time and come to questions. Yes. So thank you all for coming, and enjoy Strange Loop.